Okay, so hello and welcome to my presentation on this problem regarding the roots by graphical method, bisection, and false position method. Of course, with the formula, I have simplified that function in terms of h, and then we less here the requirement of 5 meter per second. So this function is broken down into several cells here. First, we place here the constant, the g, 9.81 meter per second squared, and the length is equal to 4 meters. Then I have here a column for the h, a column for square root of 2gh, then a column of square root of 2gh all over 2l, its hyperbolic tangent, and then finally the function of h. I have considered here a height ranging from 0.5 up to 2.7. And after getting the values, we can see here that the point where the curve will intersect 0 is nearest to this value in between 2.5 and 2.6. And we can actually see that in the graph, we have here the graph that is crossing the 0 line nearer to 2.5 value. And by this, I have considered a more precise scale or range of scale in order to come up with a nearer value to 2.5. Then I have considered a range from 2.5 up to 2.55. Then come up with a value nearest to 0, 0.011 when h is 2.55. So by this, again, I have considered a more precise scale in order to have more precise value for h. So we can see that in the graph, we have a value that is between 2.54 and 2.55. So finally, we have the more precise scale 2.541 up to 2.545. We can see here that the nearest to this value of 0 is in 2.545, because if we're going to extend this further, 2.546, it will go away to the value of 0. Okay, so the nearest is so far is 2.545 for this. And we can actually see that in the graph we have here 2.542 and 2.543. So it is in between this. So the nearest XR is 2.545. So that's it for the graphical method on this problem. Okay, for the bisection method, we have to reflect iteration, the lower limit, the upper limit, and the average. So here we are going to have several trials in order to come up with a function of XR wherein our estimated error is 1%. So we note here that we do not have any given true value. So having my initial XL and X upper 0 to 2, we have an average of 1. Then we get the function of L and the function of R. We also consider true error, estimated error. So we are not using the estimated true error because again, we do not have any given true value here. Okay, for the second iteration, we need to test our lower limit if we are going to use XR or XL. So that is tested if function of L times function of R is greater than 0, then we adopt XR. Otherwise, we are maintaining the original lower limit. So similarly to upper limit, we are going to test that, but this time the product of FL and FR, if it is less than 0, we are going to adopt XR. Otherwise, we maintain the upper limit. We shall now get the first set of the iteration. we have a 33.33% way for 1% here. So we're going to continue up to the 7th iteration. So we have between 6 and 7, we have 1.58 and 0.78. So the range is quite uh, quite far to 1%. So perhaps if we can increase the range, because the range is from 0, if we could increase the range from 0 to 2, then we will have perhaps a more precise value. And then from that, I have also considered a range of 0 to 3. I have adjusted my range now, and then the 7th iteration, we can see that we are getting nearer to 1% estimated error. So it is between 0.91 and 1.81, and as we can see, the value is 2.57 and 2.55. So it is between 2.55 and 2.6 perhaps. And then finally, I have set my lower limit and upper limit to 2.5 to 2.6. And by this one, on the third iteration, I have obtained, and on the second, I have obtained 0.99. That is actually the most nearest to the value of 1%. Because if we continue to the third, the estimated error will go farther to 1%. So this suggests that your root is 2.525 at 1% estimated error. So this is for the bisection method. Okay, for the false position method, we have a similar procedure to that of the bisection, but this time we need to involve the function of r derived from xr. And instead of the average of the upper and lower limit, this time we are going to use this formula for the xr. Again, we place here the constant. The acceleration due to gravity is 9.81 and the length is 4 meters. We reflect xl, xu, and xr. And this time xr is derived with this formula. Okay. So here we have the function of L derived from XL. We also have the function of U derived from XU, and the function of R that is derived from XR. Now from the second iteration, just similar to the procedure on bisection, we are going to test the lower limit, wherein the lower limit is tested. We multiply the function of L and the function of r. If it is less than or greater than 0, then we adopt xr. Otherwise, we adopt or we maintain the original lower limit. So similarly for the upper limit that is tested, wherein if we multiply this one and if the product is less than 0, we adopt xr. Otherwise, we maintain the upper limit. And then copying all of the cells up to the 7th iteration. Iteration 6 and 7 have consistent values, 2.542 and 2.542 for the XR. So this suggests that the value of the root is 2.542 at 0% error. So we cannot find here values for an estimated error of 1%. That is setting up XL and XU to 0 from 0 to 2. So even though you have set these values from 0 to 2, your equation or your values reflected a value that is greater than this. Even if you are going to change your XL and XU, it will always suggest that the value is 2.542. So I think This is for the false position, and thank you for listening.